Hello everyone! This week is going to be dedicated to Fourier. First, we're going to be reviewing a little bit of Fourier series, and then we're going to bridge the gap between Fourier series and Fourier transform. And that is a very interesting topic that we're going to develop quite a lot during this week. So let's start with a fairly quick review of Fourier series that we have introduced last week. So we stated that we can rewrite a periodic function between minus L and plus L as a sum of a constant a0 times phi 0 x plus an infinite sum of sines and cosines with some frequency that is embedded in the kn and some coefficients in front that is either an or bn. Or we can write the same thing as a by infinite sum. So an infinite sum goes from 0 or 1 to infinity. A by infinite sum goes from minus infinity to plus infinity. So a by infinite sum of exponential functions with purely imaginary exponent. In some senses, this is fairly similar to Taylor series. In Taylor series, we take a middle point, an x0, a point in which we know more information, and we start approximating the function with a combination of its derivatives. And if the function is analytic, then we have a representation of the function itself in the neighborhood. Here we're doing something along those lines, having a representation of our function as an infinite series. What are the advantages of using a Fourier series over a Taylor series? Well, a Fourier series deals with sines and cosines. What is the advantage is that sine and cosines are bounded. They deal between minus 1 and 1. While when we're dealing with Taylor series, polynomials are not bounded. So when we are interested in physical phenomena, often sine or cosines are more interesting to deal with than polynomials because of this bounded behavior. And the other interesting thing are that sine and cosines are orthogonal. So we know how they behave with respect to inner products. That is not true with polynomials. The steps we took in order to build up our Fourier series is that we have been studying Fourier-Liouville problems first as a general statement. They have this specific form that we have to look forward to with some specific boundary conditions. We reformulated it as an eigenfunction problem on a self-adjoint operator. So we defined this operator h that takes a function y and returns another function. We can prove that it is self-adjoint, so it respects some behaviors with respect to a given inner product. And we can reformulate the self-adjoint operator based on eigenpairs, where we took care of renormalizing the eigenfunctions. If that is the case, with this background, we can look at a very specific Sturm-Liouville problem. That is this y second from lambda y equals to 0. We introduce the periodic Sturm-Liouville problems that have periodic boundary conditions both on the value of the function and the value of the derivative. And in this new function space of periodic functions, we study this Sturm-Liouville problem finding eigenvalues that are some multiple of pi, not integer over L, and eigenfunctions that are sine and cosines. So we can now state that any periodic function of period 2L can be rewritten as this infinite sum. And what is interesting with the background we have about self-adjoint operators is that we have full control of all the coefficients that go into the formula. So we can actually compute these coefficients explicitly as far as computing integrals is possible. So we know that a0 is just the mean of the function f on the interval, and an and bn are also just integrals that we can compute from minus L to L of our functions times either sine or cosine. Or we can approach it from the equivalent perspective of looking at exponential functions with imaginary exponent. And yeah, also here we have either a representation of the coefficients based on the real coefficients of the sine and cosine series, or an integral formulation. Notice here that when we're looking at the integral formulation, Cn is the integral from minus L to L of fx times e at the minus I, k, and x. While when you're writing the infinite series, Cn is paired with e, I, k, and x. So you have to notice that we are looking at complex conjugate exponents. This is normal if we are being a bit more careful when looking at inner products. But we're not going to go there. Just remember that there is this minus sign appearing in the exponent.